Okay, so our lesson today is going to be relatively short. We're only really looking at two different types of problems and two applications of these radians. One of them has to deal with the arc length. So we already talked about the arc length and how that relates to our theta value in radians. So like a 45-degree angle really represents the radian measurement of pi over 4, and that's really then like the intercepted arc length of our unit circle. So like our angle forms with our unit circle, and then like there's that piece. So let's see, if here's my theta value that I have, it intercepts here in our unit circle in like this piece, and this piece is represented with our intercepted arc length, and that really corresponds to kind of like our theta value that we're looking for. So like a 45-degree angle really is our S value, which is pi over 4, so we can just represent like sine of pi over 4 as sine of 45 degrees, so both of our answers then are root 2 over 2. That's the big idea. So on our unit circle, our S really is like our theta value, but if the radius is not equal to 1, which on the unit circle it is, then our S is equal to R times theta. So this is kind of our important concept for today. And we could go through and kind of like derive this and see where this comes from. But all I really want to mention with this is kind of draw a picture to show why this R value is actually there. So if I have my unit circle, here we go, like that, and I have some angle measurement, like that, that's a terminal side. This is my intercepted arc length for S. But if my radius is not just 1, so like if this piece isn't 1, maybe it's 2, then I can also have a circle that kind of looks like this. So that wouldn't be necessarily 2, but this now is my radius, and then this is my intercepted arc length. So my intercepted arc length, my S value, is going to be more than the one that was on the unit circle of just 1. So like now this is looking at, I don't know, a length of 2. And so it goes up by a factor of 2 as well. Like this is now, this arc length is going to be twice as big if the radius is twice as big because I'm drawing a bigger circle. So what we're looking at is like concentric circles that are built on that. There's one thing that I want to mention is that this theta value that we're looking at, if you're going to leave it in this form, because there's other ways to look at that same kind of idea or to find the intercepted arc length, but in this form with this equation, this theta must be in radians. Under no circumstances should we plug in a value in degrees in this equation. You will not get anything that actually makes any lick of sense. Okay, so the application to that is with this gear problem. So we have two gears, they're connected by rotating. The smaller gear has a radius of 4 inches, so let's just make this one the small gear. That's 4 inches. And the larger one has a gear of 7 inches. So we're looking for the angle in degrees through which the larger gear has rotated with the smaller gear when the smaller gear has made half a rotation. So if I think about this is my smaller gear. My smaller gear has started here, and then it's rotated half a rotation. So its theta value that it's rotated is pi, because we're looking at 180 degrees, which is pi, corresponds to pi. So it's like half of our rotation there. If this rotates 180 degrees, that doesn't mean that this bigger gear will rotate 180 degrees also. It actually rotates a little bit less than that because it will take more to rotate a smaller gear. If you think about like if I had a very, really small gear on this and I'm rotating, what I'm really talking about is some length, some arc length that is going around our circle. So if you like imagine a clock and the gears on the clock, if I rotate a gear that's really small a little bit or a large amount, then a bigger gear that's connected to it will only move slightly. So the rotation of the amount of degrees won't match with the different size of gears. But the thing that will match, since they're connected, is how far around our gear we've rotated. And that length around my gear is my arc length. So what this really boils down to, this gear problem, is that the arc length of the small gear equals the arc length of the large gear. Okay, and we're solving then for the angle, the theta value of rotation. So let's talk about the arc length of the small gear for a second. That's S. And I know that in this formula that S is really R theta or theta R, either way. So my radius of my small gear is 4, and the degree of rotation is pi. I don't know about this one. I don't know, at least in total, but I do know that my radius is 7. I just don't know my theta. And that's what I'm trying to find, is the rotation that I have. So if my small gear equals my large gear, if these S's are the same, then I can use substitution, or I can just really set these things equal to each other. So I get this equation, and I'm solving for theta. So I divide both sides by 7, and I get this theta. So this would be my answer, my rotation in radians. And I'm going to convert that and find my rotation in degrees. Because I think some of the ones in your homework or your practice will have it already in degrees, so you might have to convert back to radians and then convert. Actually, since it's a ratio, and if you set them up this way, this one, it won't actually matter if you use radians or degrees. Just know that like you're getting out the same unit. But to make your life easy and to not confuse you anymore, I would always just stick with radians. This entire chapter, every time we talk about any of the formulas that we use, it's always going to be in radians. But if I do want to convert it into degrees to get my answer back out, because they tell us it's made half a rotation, but in your answer, in your homework or practice, it might say it's rotated 20 degrees. So you would probably want to have the answer at the end and also degrees, because that way you can kind of match your units. But you'd have to convert it to radians and then convert back. So we're going to convert this, long story short, to degrees, which we found out yesterday. We multiply by 180 over pi so that our pi's cancel. And I'm just going to find a decimal approximation for that. So 4/7 times 180 gives me approximately 102.86 degrees. And again, that should make sense, because if I'm rotating the smaller gear 180 degrees, this larger gear should only rotate, or should rotate less than that. It will take a lot more degrees to rotate something of a really large gear, the same length that we're looking at. Or in other words, I guess if I want to cover some distance, like you should think about like the Earth in the rotation. So the Earth is rotating at some speed, and we're covering some distance, but it's so big that like we don't really feel that we're moving, even though we are. But like if we're using that same speed or covering the same amount of rotations in a much smaller scale, that thing would be spinning really, really, really fast. So that's kind of the idea, is that like it's still covering the same distance that they're traveling around my circle, but the degrees in rotation, or the amount of rotations that happen, will be a lot smaller with a bigger radius, because a bigger radius produces a bigger arc length. Hopefully that made sense. And the second part of today is about the area of a sector, which is just a section of a circle. And we're going to come up with kind of this, not really a derivation, but I just want to talk about like the area of a whole circle. So area of a whole circle is pi r squared. And if I were going to like come up with maybe the area of a semicircle, which is half a circle, I would take pi r squared and I would divide it by 2, or in other words, 1/2 pi r squared. And if I were coming up with the area of a quarter circle, I would do 1/4 pi r squared. And if I were coming up with the area of a third of a circle, I would do 1/3 pi r squared. So all we're really doing is taking this factor and multiplying it by our area, which is really the area of this sector that we're finding. So the area of a sector then is this ratio, whatever it is, times pi r squared. Usually this ratio that we're given is in terms of some fraction, but sometimes we are given some ratio in terms of a radian measurement or a degree measurement. So for this one, like this is obviously 3/4 of a circle, but this could also represent 700 or 270 degrees or 3 pi over 2 radians of our circle too, because it just depends on like where we are on our circle and then the intercepted arc that's located with that. So we could write this instead of a ratio of amount of a whole. Amount of a whole could be like some theta in degrees out of our entire whole degrees, which would be 360 times pi r squared. Or if I want to do this in radians, it'd be some theta out of 2 pi, because it's some measurement out of 2 pi, which is our entire unit circle or our entire 360 degrees. It's some part out of some whole. So same thing here, some ratio, some piece out of a whole. If we already know the ratio, then we're golden, but if we don't, if we know only the radians that it's located in, then we can find that by taking it out of 2 pi. But the nice thing about this one is that it reduces down, so our pi's will actually end up canceling, and so we'll have 1/2, so it'll be this ratio here, theta, which again is in radians, times r squared. So overall, the area of a sector is 1/2 pi r squared. Oh, I said pi. 1/2 theta, and this theta is in radians. I'll tell you now that you don't have to memorize these formulas. They should kind of make sense, but you don't have to memorize them for the test or the quiz. We just have to really know how to apply them and make sure that every time that we're applying one of these formulas, our theta is in radians. It's super, super important. So we're just going to do one example. We're looking for the area of a sector, which again I'm going to write out the formula for it. It's 1/2 theta r squared. If the radius is 14 meters and the length of a rotation, which is our ratio here, or arc length, intercepted arc, our theta value, our degree, whatever, or our amount of rotation is 2 pi over 3. So that's going to go into our formula here, 2 pi over 3. And then our radius is 14 squared. For this one, since we're actually just going to leave pi in our answer, so let's see, I'll have our 2's 1/2 and 2 will cancel out. 14 squared is 196. So I'll have 196 on the top. I'll have a pi in the top and 3. So this would be my area of the sector. So what they're actually saying, just as like a visual, if that helps you, they're saying that we have this much, because here's pi over 3, that's where it's located. We have this much of our sector. So we're finding like the area of this piece of a circle, which we don't know what the ratio is, but we know that it's like 2 pi over 3 out of the entire 2 pi, and then we multiply by pi r squared, so the pi's cancel, and we can just really use this basically as the ratio including pi, like 2/3 pi r squared. Anyway, that's the idea for that one. So there's two kind of big concepts for today. Was the gear problem, which the intercepted arc length of the small gear equals arc length of the large gear, and then the area of a sector, which we just plug in basically the amount of rotation that we have, and then use our radius for a circle. So I know this is kind of a hot mess at the bottom here, but we do have a quiz on Monday, and this is only on the radian measurements from yesterday. So like evaluating sine of pi over 3. That's what you're getting quizzed on Monday. You don't have to memorize all of them. You'll have a calculator, so if you want to convert everything, you can. You might not have time to convert everything, so it might be a good idea to know like some of the big ones that we have, but then you also have your calculator there, so you can use that to help you if you do get stuck or you're second guessing yourself. That's on Monday. On Tuesday, I'm hitting you hard next week. We have 2 quizzes. One is going to be on this lesson, the radian measurements, so the area of the sector, and then the area, the gear problem. And then your second one is going to be on memorizing the unit circle radian measurements. Now that one, again, is going to be timed. It's only 3 minutes. And they're all going to be mixed up, so you won't have time, and you won't have, like, it's not just memorizing the list down. Some of them you'll be given the degrees. You'll have to come up with the radian measurement. Some of them you'll be given the radian measurement. You'll have to come up with the degrees. And then there'll be like a short little quiz on the radian application that day as well.